Hello everybody, this is Dr. Wright. Welcome back. We're going to be doing our third online module for ManEc/Fin 453. You can see the title of the third online module is Continuously Compounded Returns and the Basics of Return Distributions. Let's find ourselves in the map. We are on the third module, as you can see right here. Let's also remind ourselves what the objectives are for this Excel training for all of these online modules. We'll only do this maybe one or two more times and then we'll assume that you have it. But let's just remind ourselves quickly. The goal is to review, teach, and invite you to apply important principles and models from financial theory in order to give you opportunities to enhance your proficiency in the following Excel skills. Today we're going to be focusing on basic Excel functionality, more focused on finance review today, but it will also give you some practice in terms of just simple basic functions in Excel. The goals today: we want to review the basics of how to calculate continuously compounded returns, we want to review the basics of return distributions, and we want to give you an opportunity to calculate and interpret basic summary statistics for a real-world stock or index. So let's begin by refreshing our memories about how we calculate average returns. These are all things that you've been exposed to, so this will be a review. We'll move through it quickly. There are three common methods. There are several other methods, but these are the three most common methods that are used to calculate the average return for an asset. There's the arithmetic average, the geometric average, and the continuously compounded average. Let's spend just a minute reminding ourselves how we calculate each of these three different types of average returns. When it comes to arithmetic average returns, this is the simplest method. For an asset with n return periods, step one is to simply calculate the simple returns in each period, and I'm going to refer to a period as period t. So in period t, you calculate the simple return as the price in that period t minus the price in the previous period, t minus 1, divided by the price in the previous period, t minus 1. Once you've done that for all of the n periods in your data set, then you simply calculate the simple arithmetic mean of these n periods by adding up all of the simple returns and dividing by the total number of periods in your sample set. I'm going to try to give you a demonstration for each of this just to refresh your memories. Let's jump over to our Excel spreadsheet. I'm going to use Walmart from January 2nd of 1995 through June 30th of 2012. You've already seen this, so I'm going to move through this quickly. I'm going to view the macro, run the macro. It's going to pull up this data. First thing I'm going to do is sort it from oldest to newest. And then I'm just going to calculate the returns. So again, all I would do is I would take this period's return minus the previous period, divided by the previous period. I would shoot that all the way down, turn it into percents, give it a couple decimals, and then I might want to center all of that. So then, to get the arithmetic average, so we're looking for average returns, to get the arithmetic average, all we do is take the average of all of these individual daily returns. So we do that, and we see that the average daily return for Walmart is 6 basis points, specifically 6.4 basis points. So very simple. That's the most straightforward way to calculate average returns. The second way to calculate average returns is to calculate geometric average returns. Recall from basic time value money concepts that the future value is equal to the present value times 1 plus the periodic rate raised to the number of periods, assuming there are no periodic payments. Again, R is the periodic rate, N is the number of compounding periods. Simple algebraic manipulation allows us to determine that we could infer the periodic rate if we knew the future value, the present value, and the number of compounding periods. So we could just transform the formula, and we can see that the periodic rate would be the future value divided by the present value. That ratio then raised to 1 over the number of compounding periods. We need to be careful about something. This is not the number of days or months or years of prices. It's the number of days, months, or years for which there are compounding periods. And I'll try to make this distinction for you as we do an example. So if we want to get I'm sorry, and then after you raise the ratio to 1 over n, you subtract 1. So you just need the ending value, the beginning value, take that ratio, raise it to the 1 over the number of compounding periods, and subtract 1. Let's go ahead and execute this over here for Walmart. So to get geometric average returns, first off we need the future value, or the ending value, which is down here at June. So we can see that the last trading day in June of 2012, the price was $68.96. We're going to divide that by the very first price. So that's our ratio. Then what we need to do is raise that to the 1 over the number of compounding periods. Lots of people miss this and overlook it, but it's a very simple idea. However many days worth of prices I have, there will be one less day worth of compounding. The reason is it takes an initial day to get my first compound. So to get this first return, it takes 2 days. So what I'm going to do is I'm going to count up all of the days that I have. And I'm going to subtract 1. Now also, make sure you get your parentheses right. I need that count minus 1 in the denominator right there. So what I have is future value over beginning value raised to the 1 over the number of days minus 1, since I don't have a return calculated for the first day. And then the last thing I need to do is subtract out 1. And then just copy and paste the formatting. And so you can see that the arithmetic average return is 6.37 basis points. The geometric average return is 4.8 basis points. We'll talk in just a second about how those are different, but I want to show you the third way that we can calculate average returns. The third method that we use to calculate returns are known as continuously compounded average returns. Please recall from time value of money principles that when dealing with continuously compounded returns, the future value is the present value times E raised to the periodic rate times the number of periods. Now we can again do an algebraic manipulation, which is a little bit more complex but not terrible. When we do the algebraic manipulation, we can infer the continuously compounded periodic rate of return by taking the natural log of the ratio of the future value over the present value divided by the total number of periods. Over here for Walmart, if we wanted to do continuously compounded returns, that would mean we need to take the natural log of the ending value divided by the beginning value, and divide it by, again, the number of compounding periods. So count, add all that up, subtract 1, but again, be careful with your parentheses. That can really trip people up. And so you can see that the continuously compounded returns are 4.79 basis points per day, which is very, very similar to the geometric average returns. Now, I want to show you one other thing related to continuously compounded returns. We can get that exact same result using a slightly different method. Here is the slightly different method. Instead of doing this formula, what you can do is every period calculate the continuously compounded return. How would you calculate the continuously compounded return every period? Well, it would just be the log, natural log, of the price in that period divided by the price in the previous period. It's this formula, every period. The only difference is if you're doing it every period, n only equals 1. So you do this every period. You take the natural log of the ratio of that day's price or that month's price divided by the previous day or previous month's price, the previous period's price. So it's this period's price divided by the previous period's price. Take the natural log of that. So let's do that over here. So I would take the natural log of this price divided by the previous day's price. I would shoot that all the way down, turn it into percents, and again center it. Okay, then the second step would be to simply take the arithmetic average of all of those individual continuously compounded returns. So we would just sum up all of those individual continuously compounded returns and divide by the number of individual returns. So we can get this exact same result by doing this. Taking the average of all of these individual continuously compounded returns. And you can see that we get the exact same result. So those are the three most common ways that we calculate average returns. Now let's talk for a second about the trade-offs. What are the advantages and disadvantages? Well, the arithmetic average is simple, it's intuitive, and one of the things that we like about the arithmetic average is it gives us a ton of observations, which allows us to calculate a mean and a standard deviation, which means we can interpret statistics and even apply statistical tests. What we don't like about the arithmetic average, however, is that it fails to capture the effects of compounding, and that's a pretty significant disadvantage. What do we like about geometric average? We like the fact that the geometric average return now takes into account the effects of compounding. What we don't like about the geometric average is it doesn't give us a ton of observations. Remember, to do the geometric average, it's one calculation, which means there are not a whole bunch of observations. We don't calculate a mean and a standard deviation. If we don't have a standard deviation, it becomes much more difficult to interpret the statistics, and we cannot apply statistical techniques. What do we like about continuously compounded average returns? We love the fact that it captures the effects of compounding. In fact, it most accurately reflects what really happens in the stock market. Stocks trade continually, therefore continuously compounded returns are the most accurate reflection of how trading actually occurs. Also, if we calculate continuously compounded returns using this methodology over here, we likewise get a bunch of observations that allow us to calculate a mean and a standard deviation, which allows us to apply statistical techniques, which is very beneficial. The only downside for continuously compounded average returns is they're not as intuitive and they're not as simple as some of the other options. But hopefully what you can see is that continuously compounded returns offers us the best of both worlds. It offers us statistics, specifically mean and standard deviation, that we can interpret and also will allow us to apply statistical techniques. But it also captures the effects of compounding. So it takes the advantages of both of the other two methods and combines them into one. For that reason, we really like this method, because it captures compounding and we can interpret basic statistics. So we're going to use continuously compounded returns, which means every period we're going to calculate the continuously compounded return, then we'll take the arithmetic average of that. Now, one note, in order to annualize continuously compounded returns, it's very simple. In order to annualize the average return, you just multiply it by the frequency. So if you're dealing with monthly data, you take your average monthly continuously compounded return and multiply it by 12. If you're talking about daily, you take the average daily continuously compounded return and you multiply it by 250. You do the same method for the variance. Take the monthly variance and multiply by 12, or take the daily variance and multiply by 250. For standard deviation, what you do is take the continuously compounded standard deviation and multiply it by the square root of the frequency. Of course, this makes perfect sense because standard deviation, we know, is the square root of the variance. If, in order to annualize the variance, we multiplied by the frequency, then in order to get annualized standard deviation, we have to multiply by the square root of the frequency. So if you're talking about monthly standard deviation, multiply by the square root of 12. If you're talking about daily standard deviation, multiply by the square root of 250. So over here with Walmart, that's our continuously compounded daily return. In order to annualize it, we would simply take that and multiply it by 250. What if we wanted to get the continuously compounded standard deviation? Well, we would take the standard deviation of these continuously compounded returns, and then what we would do is we would multiply that by the square root of 250. And then we would simply give it some formatting help. So you can see that over my sample period, Walmart had an average daily continuously compounded return of 4.79 basis points, which annualizes to 11.98%. Its daily standard deviation is 1.77%, which annualizes to 28%. Next, I'd like to go through a refresher on probability distributions. Remember that statistical distributions are often described as a function of the first 4 moments. That terminology may be foreign to you, but I think as we talk about it, you'll remember it. The first moment in a distribution is known as the mean. The mean is the center point of the distribution, literally where you would place a fulcrum to balance the distribution. The standard deviation is the second moment. The standard deviation represents the average dispersion around the mean. Skewness is the third moment. It represents the asymmetry in the distribution. In other words, do one of the tails run out longer than the other? Kurtosis is the fourth moment of the distribution. This is the size of the tails. Kurtosis is very important because it gives us insights into the probability of a tail event. Now, we're not so concerned about positive tail events, but we're very concerned about negative tail events. So seeing fat tails would be a little bit disconcerting because it would suggest that there's a higher probability of a tail event, which could mean catastrophic negative returns. Most of you have seen the normal distribution. It's this nice symmetric bell-shaped distribution. Note that whenever you look at a probability distribution or a probability density function, on the y-axis represents the probability. On the x-axis represents the possible values that the observed variable can take. Also, we have something known as the 68, 95, 99 rule. If you're dealing with a normal distribution, roughly 68% of all observations should be within 1 standard deviation of the mean. We represent the mean with the Greek letter mu and the standard deviation with the Greek letter sigma. Again, in a normal distribution, 68% of observations, roughly speaking, should be within 1 standard deviation on either side of the mean. Also, if you're looking at a normal distribution, roughly 95% of all observations should fall within 2 standard deviations on either side of the mean. And then if you go out 3 standard deviations, that should capture over 99% of the observations. This is very helpful. This means if you're dealing with the normal distribution and you know the mean and the standard deviation, you can easily construct lower and upper bounds that can tell you where 99% of the observations are likely to fall. Note that for a normal distribution, skewness is equal to 0 and kurtosis is equal to 0, which means skewness of 0 means the tails do not run out farther on one side or the other. You have perfect symmetry. Kurtosis means that there are no fat or skinny tails. And I'm going to give you an example of violations of this 0 skewness and 0 kurtosis in just a second here. So what I've done is I've gone and calculated my own distribution. And so here's an example of a normal distribution. The mean is 7.96%. The standard deviation is 9.94%. Imagine that this could be some stock that's with relatively low volatility. And you can see that the skewness is negative 0.02 and kurtosis is 0.03. Those are virtually 0. So you can see again we have this nice symmetric bell-shaped curve here. On this axis we see all of the possible values that this variable could take. And on this axis we actually see the number. So I did 5,000 iterations, and this shows you how many of those iterations have those particular values. Let me show you now a distribution that is skewed. Again, I did 5,000 iterations. Over here on the y-axis, this tells you how many iterations fell in this bin right here. What you can see now is we have negative skewness going on. We have an average of 4%, standard deviation of 15%, but we have a little bit of negative skewness. You can see that the left tail runs out much longer, there's even some down there, than the right tail does. This is a negatively skewed distribution because that left tail runs out so much farther. Now I'm going to overlap the skewed distribution with the normal distribution. You can see the blue is the normal distribution. It's a nice symmetric bell-shaped distribution compared to the red distribution, which has this left skewness manifested as the left tail, the negative tail running out much farther than the opposite tail on this side. Now let me show you kurtosis. Now kurtosis is not going to be very visible in this graph by itself, but you can see this distribution has an average of 7.99%, standard deviation of 11%, No skewness really, but it has positive kurtosis. That's going to mean fat tails. The only real way to see this is if I overlap the normal distribution with the leptokurtotic distribution. You can see a leptokurtotic distribution has fatter tails. What does that mean? Out here in the nether regions of the distribution, out in the tails, we have higher, bigger, fatter tails for this leptokurtotic distribution. How do you interpret that? That means the green distribution has a higher probability of a tail event. If we were talking about stocks, the green stock would have a much higher probability of extreme positive and negative returns. Something we care deeply about because we understand that episodically in the stock market we do observe catastrophes and crises, and so it would be very important to understand what type of tail risk a specific stock poses. So what we want to do today is I'm going to do this for Walmart, but I want you to do it for the S&P 500. We're going to simply calculate the continuously compounded returns. We're going to calculate some summary statistics. We're going to look at mean, standard deviation, skewness, kurtosis. We're going to come up with the 68, 95, 99 upper and lower bounds, and then we're going to create a histogram and try to actually draw the distribution. Again, I'm doing it for Walmart. You're going to do it for S&P 500 from 1960 to 2012. Let's go ahead and dive into it. So I'm going to go ahead and delete everything that I don't need here that I've been dealing with. I don't need any of that. I don't need that return, and I don't need any of this. Now, ultimately, we're going to want your file to look something like this. So we want to calculate the mean, standard deviation, skewness, and kurtosis. So we want mean, standard deviation, skewness, and kurtosis, daily and annual data. So let's go ahead and start with that. So I'm just going to take the simple average of all. Remember, these are the individual daily continuously compounded returns. In order to get the overall average continuously compounded returns, we just have to take the simple arithmetic average. So I'm going to do that. I'm going to take the simple arithmetic average, and we'll give it a couple of decimal places, and we'll center all of this. So again, and that's something we already saw, we know that the average daily continuously compounded return is 4.79 basis points. We know we can annualize that by simply multiplying by 250 since we're dealing with daily returns, and give it some formatting attention. We'll also go ahead and calculate the standard deviation of these daily returns, and we'll annualize that by multiplying it by the square root of 250. And again, we'll just give it some formatting TLC. Now, we next want to get the skewness. We just use the skew function in Excel, highlight all of our daily returns, and we can see that it has skewness of 0.1, which is not really much. That tells me that there's not a lot of skewness in the daily returns to Walmart. Next, we look at kurtosis. We use the kurt function. A little bit of formatting help, and we see that it has positive kurtosis of 3.52. Remember, a normal distribution would have 0 skewness and 0 kurtosis. One of the hallmarks of the normal distribution is that it is entirely defined by the mean and the standard deviation. Since we have strong positive kurtosis here, that's called leptokurtosis. Since we have a leptokurtotic distribution, that suggests that there are higher probabilities of tail events or extreme high or low returns to Walmart on a daily basis. We're not going to try to annualize those. There's no need. Let's go ahead and format this real quickly. Okay, the next thing that we want to do is just create the 68, 95, 99 lower and upper bounds, and we're going to do this for annual returns. So let's do this, 68, 95, 99% bounds for annual returns. And we're going to have a lower bound and an upper bound. And we're going to want to start with the 68, then the 95, then the 99. And again, we're going to do this for annual returns. So to get the lower bound for the 68%, we would just take the average return and subtract out 1 standard deviation. To get the lower bound for the 95% bound, we would take the average and subtract out 2 times the standard deviation. To get the lower bound for the 99th, we would take the mean and subtract out 3 times the standard deviation. The upper bounds are just the opposite, so for the 68, we would take the average and add 1 standard deviation. For the 95% upper bound, we would take the average and add 2 times the standard deviation. And for the 99% upper bound, we would take the average and add 3 times the standard deviation. No need to have all those decimals, so we'll just give this a little bit of TLC. Center some of this. And we can reduce that down a little bit. And again, we can give it some formatting assistance. Alright, the next thing that I would like us to do is I would actually like us to paint the distribution, draw the distribution. Now, there's a couple ways you can do this in Excel. You can actually do it through the data analysis. You can do data analysis, and it has a histogram option. I don't personally like that because it's not refreshable. So if we update our data for any reason, that histogram wouldn't automatically update. So I'm going to show you a method so that your histogram automatically updates. So here's what we're going to do. Let's just label it. And we're going to do this with daily returns. So we need to get our bins. And I'm just going to do 25 bins. So let's go to the home and we'll just fill this in using a series. It's a column. And it's going to go from 1 to 25 like so. And we can center all that. Now, what we have to do is we have to come up with breakpoints for our histogram. For instance, we can see that they have all sorts of returns. We have to come up with breakpoints that we can start dropping these daily returns into bins. So in order to do this, this is how I'm going to do it. I'm going to go and get the minimum value that I see from all of the daily returns. That's going to be our lowest bin. You can guess that our highest bin is just going to be the maximum value, like so. Now all we have to do is fill in the middle here. So what we want to do is go from a low of minus 10.23% to a high of 10.49%. Parenthetically, you can see the symmetry in the distribution just with the high and the low. Lowest daily return they've experienced is 10.23, negative 10.23, and the highest daily return is 10.49. So we see some nice symmetry emerging right there. Once we have the minimum bin and the maximum bin, all we have to do is fill in the steps in between, which is relatively straightforward. All we're going to do is take this previous bin value and we're going to add to it a small amount, and that small amount is simply going to be the difference between this maximum and this minimum divided by 24. Now think about the logic behind that. We're starting at 10.23%. Ultimately, we need to get to 10.49%. So F39 minus F15 represents the distance we have to travel. How many steps do we have to take to travel that distance? We have 24 steps to take. So every step that we take, we have to travel F39 minus F15 divided by 24. Now, you have to lock in the F39 and the F15, and then just gently pull this down once those are locked in. And you can see we have a nice monotonic movement from this minimum up to this maximum. And again, we can go ahead and center all that. Alright, so what we want to do is we want to count up how many of our daily returns fall into each of those bins. It's pretty simple. All we have to do is the COUNTIF function. And specifically, we're going to count up any of these daily returns and lock that in. If they are less than or equal to this bin value right here. Close up the parenth, and we should be able to shoot that all the way down the line, and we're going to have to make a modification, and I'll show you what that is. So what we need to do now is, for instance, in this bin right here, it's capturing all of the returns that are less than 9.37%. But we don't want to do that. We only want to capture the returns that are less than 9.37% that are not in a previous bin. So what we need to do is in each cell we need to subtract out all of the bins that we've already previously accounted for. So that 3 includes that previous 1, which means there's only 2 unique observations in this bin. Just like there aren't really 5 observations in this bin, these 3 observations are being captured there and we don't want it. So there are also only 2 unique observations in this bin. It's a very quick fix for that. You just come in right here and subtract out the sum starting in that cell, going through that cell, and lock in the first G15. Now, that's going to seem strange. Let me explain it to you. When we do count if, and we highlight all of this, and we only count it if it's less than or equal to this bin value right here, that originally gave us 3. But we knew that those 3 actually captured the 1 that we had already taken into account in the previous bin. So all we're doing is trying to subtract out any observations that we've previously captured in earlier bins. So the way we're going to do that is we do the sum function starting in this first cell, going through the first cell. Now, why lock in that but not lock in that? Here's why. When you drag it down, watch what happens. Now, we're taking the COUNTIF function minus G15 through G16, which is exactly what we want. Drag it down one more, and you can see now it's subtracting out G15 through G17. So by structuring it the way we did, we can drag the formula down and it's going to subtract out all previous bins. So we'll do that. Now you can double check and make sure you've done it right by adding up all of the observations. So let's just add up all the observations and we get 4,406. Just double check that by highlighting all of your daily returns, and you can see down here there are indeed 4,406. So we have in fact captured all of the observations. Let's center it. And now let's figure out the probabilities or the percent. In other words, what percent of our observations fell in each of those bins. That's very simple. Just take the count and divide it by the total number. Lock that in. Copy and paste that formula down. Turn it into percents. And center it. So this tells us what percentage of all of our observations fell into each of these bins. We might want to go ahead and just give this some formatting TLC while we're in the vicinity here. All right, now the last thing I want to have us do is draw this distribution. So all we're going to do is we're going to insert a columnar chart, and we're going to simply select the data. So we just went to Insert, Chart, pick the bar chart, and now we're right-clicking on the chart and selecting Data. And we're going to add in the Walmart distribution. Again, these are daily returns. And what we want are the probabilities or the frequencies. So this is a frequency distribution, so we want the frequencies, and now we need to edit the x-axis. These are the bins right here, so highlight those for your x-axis. Once we do that, we just slide it up, make it a little bit bigger so it's more visible. And we probably don't even need to have that, and we should label it. So this is a Walmart frequency distribution, or you could call it a daily return distribution. So let's do that. We'll call it the Walmart daily return distribution, 1995 through June 2012. And now let's just talk about what we see and what it means for us as investors. First off, we know that the average daily continuously compounded return is 4.79 basis points, which annualizes to 11.98%. Its daily standard deviation is 1.77%, which annualizes to 28%. We like the fact that we don't see much skewness. It's a very symmetric distribution. We can see that playing out here. Specifically, neither of the tails run into the distance relative to the other. So we see good symmetry. That's nice. What you'd want to watch out for is negative skewness, right? Because what does negative skewness represent? Negative skewness would indicate that there's a higher probability of experiencing extreme negative returns than extreme positive returns. Clearly, we wouldn't be interested in that. We are, however, slightly concerned about this kurtosis. It's positive kurtosis, which means the tails are fatter than normal distributions. What does that mean? That means that these upper and lower bounds cannot really be trusted. If it's leptokurtotic, meaning the tails are fat, that means we have a higher probability of being out in the tails than you would have under a normal distribution. So this 68% upper and lower bounds can't really be trusted. In other words, we have a higher probability than just 32% of being outside of these bounds. And we have a higher probability than just 1% of being outside of those bounds. So the whole point of this today was just to help you refresh your minds about continuously compounded returns, why we like them, why we use them, and give you an opportunity to calculate some basic summary statistics, to do some analysis of it, and also to create a histogram. A histogram, I might add, that's refreshable. So I wish you the best of luck with the assignment. Please remember that you're doing it for the S&P 500 from 1960 through all of 2012. We would like it to look exactly like this, and please take a moment to interpret what you see. Do you see skewness? Do you see kurtosis? What does that skewness and that kurtosis mean for these upper and lower bounds that you've created? Best of luck with the assignment, and we will see you in Module 4.